Your class then is ready to pick up and talk about increasing and decreasing functions today. We talked about increasing and decreasing functions a little bit a year ago because we did talk about them in Algebra 2. They're in that very first unit, okay? With the idea of increasing and decreasing. A function is considered increasing as the x values increase. So when we talk about x values increasing, that's as you move across the paper to the right. If the x values increase, and so does the y, that's when you're going to have an increasing function. Okay? So as you move across the paper to the right, your y values are increasing, or in other words, your graph is moving upwards as you move right. Okay, a function is considered decreasing if as the x values increase, so again, that's as you move across the paper to the right, but the y values are decreasing. So as you move across the paper to the right, and we draw left to right, but moving in a downward fashion, that is a decreasing function. A function is considered constant if as the x values increase, so again, as I move across the page to the right, the y values stay constant. And so y values to stay constant as we move across the page to the right, I'm going neither up nor down, I'm just staying constant. Okay? So that's a little bit about the vocabulary, increasing, decreasing, and constant. I will say most of the time we're going to talk increasing and decreasing. It's rare that they actually do anything with constant, but that would be a horizontal section of a graph. For each function, tell the intervals on which it is increasing or decreasing. So what do we need to do here? What do you know about f of x equals x plus 2 quantity squared? Parabola? Can we all say it's a parabola at least? Can we at least get that far, right? Because there is what? X squared. We know it's a parabola, yes? What does the plus 2 do to it? Moves it left 2? Okay, so if it moves it left 2, that means that this vertex is at -2, 0. Now, in all honesty, that's all you really need to know about this graph. Could you have graphed it on your calculator? Yeah. Well, surely you could have. Whoops. Zoom 6. Okay, does that agree with what we just talked about? Yeah, it's a parabola moved to left. Okay, now we're going to talk about increasing and decreasing intervals on all of these as we start at the left. Okay, as I start at the left, what is my graph doing first? Down. As I move from left to right, so as I trace across my paper, the first thing I'm doing is I'm moving in a downward motion, yes? Which means my graph is doing what? It is decreasing. So my first interval is going to be a decreasing interval. Now, when we talk about, it says tell the interval or intervals on which it is increasing or decreasing, think in terms of x values. Okay, it's decreasing because my y values are getting smaller. But on what x intervals? So when did my graph start decreasing? Okay, so my graph is coming from infinitely left. Yes, it's coming from infinitely up, but we're talking x values, so it's coming from infinitely left. So it starts decreasing at negative infinity. When does it stop decreasing? 0. At the x value, at the location of the x value, which is -2. Okay? And what do you want to use with that -2? I would have said bracket. Now, I'll be honest. In terms of increasing, decreasing, I could go with either argument. I would have said decreasing just because are we going to touch that point? And we're going to touch that point at -2, 0, yes? So that's why we have said bracket. Now, I think you could also do parentheses and get away with it on the increasing, decreasing. Some things, like on domain or range, like if this was domain or domain, we'd have to have the bracket there. So, okay. What happens after we leave -2, 0? Yeah. As I start tracing this graph, now as I move right, I am moving up. My y values are increasing. And so now we are entering an increasing interval. At what x value did we start increasing?
-2.
At -2, right? At -2, 0, the lowest y value is 0. So -2. When are we going to stop increasing? Yeah, as we go infinitely up, we're going infinitely right. And that is positive infinity. You can use the trace function on your calculator as well, if you're unsure about something, to turn the calculator on, to kind of follow along here. I'm going to go all the way left here. If I watch my y values, they're getting lower, 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 all the way up to about -2, and then my y values get higher, higher, higher. So you can use the trace to help you along there. Okay. Then we're done, right? We traced that whole graph. Okay, let's try B. Well, what do you know about B? Is it a parabola? You know what the graph looks like? No, so what should we do?
Graph it.
Let's graph it. Your graph should look like my graph when you get done graphing it. Okay, your graph doing something like that, yes? Okay, so this is going to take sections, right? I'm tracing just so I have something to point at here. Start your left side, your farthest left piece of your graph. What is the first thing that starts happening as you start tracing that graph?
You start increasing.
As I start here, it's very slow at first, isn't it? But are your y values getting higher? Yeah, y values are getting higher. So the first interval is going to be an increasing interval. Okay. On what x values are we increasing? When do we start?
Negative.
Right? My graph is coming from -infinity. And then when am I going to stop increasing? Or at what x value? Because technically we're going to be going infinitely up, yes? I'm going to hit trace here and I'm going to go off to the left so we can kind of follow what's going on here. But technically, so we're increasing. Notice my y values are getting a little bit bigger every time. Y values are getting bigger, bigger, bigger. Oh, now they're getting way bigger. Right here, back up a few, at x equals -1.5, -1.36, -1.2, -1.06. And then notice my cursor all of a sudden flips to the bottom piece. I'm not ready to talk about that yet, am I? So, what do you think? At what x value did we stop increasing?
-1.
-1. And what is here at -1? Yeah. There is going to be a vertical asymptote here at x equals -1. What's going to prove to me there's a vertical asymptote at x equals -1? What's this denominator of x squared minus 1 do for you? X squared minus 1 does what? Factors into x and x plus 1 and minus 1. Am I ringing some bells here? But what that's saying is, in both cases, those are places the denominator equals 0, yes? If they don't have factors that cancel the denominator equals 0 here, those are going to be vertical asymptotes. So when x plus 1 equals 0, that's x equals -1. There's a vertical asymptote. Where else is there going to be a vertical asymptote? At +1 over here. So this is where I will always argue, don't just look at the graph. Don't just look at the equation. Look at them together. Because as soon as I see, oh man, there's some kind of vertical asymptote happening here, by looking at my denominator, oh, I know there's going to be asymptotes at -1 and 1. So here we were increasing, starting at -infinity, up until the x value of -1. Am I going to touch -1? No, because it is a vertical asymptote. Okay, so that's one increasing section. Now, we continue to the right. So as we continue to the right, we're going to hop over the asymptote. Now where are we? We're down here. Where am I going? Are we going up again? So if we're going up, we are increasing. Where are we increasing to? Whatever that top of that parabola piece is. Okay, now, so this is another increasing section. When did we start increasing? Yeah, we're coming from the y value of -infinity. It's coming from infinitely down, but it's at the x value. We're on the right side of that vertical asymptote, so -1, and that -1 has a parenthesis because it's that vertical asymptote we didn't touch. -1 up till, I heard 0. Is it 0?
Yeah.
I say, I think if I recall, that top is at 0, 0, right? My calculator turned off, but. Oops. Yeah, the top there is at 0. So we're increasing to 0. Parenthesis or bracket on 0? Bracket, because are we going to touch 0? Yeah, we're going to touch 0 here. It's a point, not just an asymptote. It's a point. I'm going to touch it. Okay, what happens after I leave the point 0, 0? As I continue right on my journeys, I'm now moving down, which means my y values are decreasing. Okay, thoughts on this decreasing interval? Okay, starts decreasing at 0. And then it's decreasing. You move as far right as the asymptote, which is at 1. So 0 to 1. 0 again is a bracket because we touched the point 0. Are we going to touch 1? No, because it's an asymptote. Okay. Do you know what you're doing with the next section? We're going to jump the asymptote. Again, I'm starting on the left and tracing to the right. As I start left and trace to right, where am I going? We are moving down the graph. So again, we are decreasing. When did we start decreasing? This time we're on the right of 1. 1 with a parenthesis. When are we going to stop increasing or decreasing? Never. Because we're getting closer and closer to this asymptote here, yes? There's a horizontal asymptote. We're getting closer and closer to it. We're not going to touch it, though. So that's going to positive infinity. Okay. Got a little bit of an idea there on increasing, decreasing? And again, you can always use the trace feature to help track some ordered pairs to see if that will help. Okay. We're ready to talk about boundedness. Okay, boundedness is one I like, although I don't know, sometimes there's difficulties comprehending come quiz and test time. Okay, so the following of these examples are visuals of how graphs are bounded. A graph can be bounded above, bounded below, bounded, which means both, or not bounded, unbounded, not bounded, I think is the word they use. Okay, so okay, I've explained some of the visuals here, and then we'll talk about these. So this first example, notice the graph says not bounded above, not bounded below. This first graph is an example of a graph I would call not bounded. It's not bounded above because what happens right here? This graph is going infinitely up. Is there an upper boundary that it doesn't cross? And it doesn't, okay? There is no roof on this problem, so to speak. That graph is going infinitely up, so it's not bounded above. What about below? Is there a floor or a lower boundary this graph will never cross? No, that graph is going infinitely down, so this graph is not bounded below. So this graph is an example of not bounded. If it's bounded anywhere, it's not a physical line drawing, but there's like, you could draw in an invisible boundary line your graph would never cross. Okay? And in this case, there's no line I can draw in above or below where my graph won't cross it, because it's going infinitely up and infinitely below. So, not bounded. Now, this next one is an example of a graph that is bounded below. It's not bounded above because what's happening? That graph is going infinitely up. Yes, there's no roof, there's no upper boundary. What about below? Is there an absolute low point that we won't go past? Yeah, your graph won't go past that lowest point. So you could think about what I often draw in is, okay, there's this invisible line that is my boundary that my graph will not go past. And so that means this graph is what I would call bounded below, because it never goes below some certain set y value. Okay, reverse the situation. This next graph is what we'll call bounded above. What do you notice on top? I think of it as like a big M, but there's two tops. Is this graph ever going to go below, excuse me, is this graph ever going to go above the top of that M? No. So I could think of it as there's an invisible boundary line that my graph will not cross. Now, is it bounded below? And the answer, is no, because my graph is going infinitely down. So there's no floor I could draw that it won't cross, or no bottom boundary. And then this last graph. This last graph is an example of bounded. Is there a top point it never goes above? Well, those are the highest points, yes. And what's different about these endpoints here? They are specifically endpoints. They're not arrows. So does this graph extend indefinitely? No, it stops right there. So those are my highest points. We can't go across those highest points. What about down on the bottom? We have a low point we can't go past. So this graph is what we call bounded. It is, when we talk about bounded, it's bounded both above and below. You will hear in the book, I think they say bounded on its domain is the vocabulary they use. That's just their fancy speak for saying bounded. So if you get to the homework and the homework's asking you to pick bounded above, bounded below, not bounded, or bounded on its domain, that's just fancy way for saying bounded. Okay. Identify each of these functions as bounded above, below, bounded, or not bounded. Well, what do you think about w of x equals 3x squared minus 4?
So,
It's a parabola, yes?
bounded, bounded below at negative.
Okay. So it's a parabola. Irrelevant is the parabola has a vertical stretch by a factor of 3. It does translate down 4. But here's the deal. How is it bounded? Well, this is bounded below. Is there a low point it will never go past? Yeah, it will never go past the y value right here. And if that graph didn't come to your brain, could you have graphed it on the calculator?
Yeah.
Yes, by all means, graph them on the calculator. So this is bounded below. And generally speaking, I'll be happy with bounded below. But what is that lowest y value it doesn't go below? Yeah, so I'm going to say bounded below at y equals negative 4. But in all honesty, bounded below is what I'm looking for there. The fact that my graph will never have a y value lower than negative 4. Okay. Do you know what this next graph looks like? You see me walking to my calculator, so you know I don't expect you to know what it looks like, right? Which one is this? This one is
4, no people.
x over 1 plus x squared.
Bounded. Yes.
So what's our claim?
Bounded.
I stink at drawing this one, but I was going to try and put a visual here. Okay. So, graph looks something like this, yes? Left and right, what is this graph doing? It is going infinitely out left and infinitely out right. But bounded is about how high and how low it goes. Is there a certain height it will never go above?
Yes.
Where will it never go above?
Yeah. Like,
The highest point, which is where in location. You don't have to give me a number, but where is it on this graph? Okay. Top of that bump there?
Yeah.
Is it ever going above that? No, because as it goes off to the sides, it's getting closer and closer to the x-axis. So if it's getting closer and closer to the x-axis, it's staying along 0. That's the highest point. Where's my lowest point? Okay. How about the valley? So I'm not just saying bump and bump because I'm like, there's some difference there, but the valley, right? You got a mountain and a valley. Those are your points. So the idea here is my graph never goes above this point, never goes below this point. Doesn't matter how far I look. It's never going to go past that. So this is what we call bounded. It is bounded both above and below. Or your book would say bounded on its domain. Okay. One last topic. This is where you get to learn a new calculator trick here when we get to the example. We're going to be talking about extrema. And I will tell you, extrema is an important vocabulary word. You need to know what extrema are. For when it comes up on a quiz or a test and asks you a question about extrema, you're not stuck like a deer in the headlights saying, what? Extrema? Huh? And in all reality, the word extrema came up in calculus today. I said, hey, when your pre-calc friends come asking you, what are extrema? You better remember, right? So extrema it's a fancy word for mins and maxes. Okay? It's described here as the hills and valleys of our graphs. Specifically, though, extrema are your maximums and your minimums. So we have what are called local maxes and mins, which can occur anywhere. Okay, and you can have multiple local mins and maxes throughout a graph. So if you've got a really curvy graph that keeps going up and down, there can be multiple mins, multiple maxes. Okay? But we're also going to talk about an absolute. And when we talk about an absolute maximum or minimum, that only occurs once on a graph. There's only one absolute max, and that is the highest and only highest point. There's one absolute minimum. It is the lowest and one lowest point of that graph. So, a few pictures. If I draw a right side up parabola, what is this vertex? It is a minimum because it's at the bottom. Specifically, though, while yes, I can call it an absolute min, while yes, I can call it a local min, because it is a local min, it is specifically an absolute min. Will my graph ever go lower than that vertex? And it'll never go lower than that point, will it? So this is an absolute min. Again, you can also call it local, but specifically it's absolute. So when I turn the parabola upside down, now what is my vertex? It's an absolute max. Because my graph will never go higher than that point. Okay, you got that? Now, let me get fancy on you. Okay. What would you call that point right there?
Local max.
Okay, it is a max. Local because is it the highest point my graph will ever go?
No.
No, because what's happening over here?
No.
My graph is going up to infinity. Is there going to be a local max? No, because my graph is going up and down, up and down. Okay, what's this point?
Local minimum.
That's a local min. And it is a min. It's only a local min because is it the lowest point my graph will ever go? No, because my graph goes infinitely down. And what else do we have here? We have another local max and an local min. Okay, you got your vocabulary? Okay. Our example here. Decide whether this given function has any local maxima or local minima. If so, find the values. State whether or not the values are considered absolute. So, what do we need to do here? Why I might suggest you might eventually know what an x to the fourth graph looks like. We need specifics here. So we are going to graph this. Everybody needs to graph this one. Because we're going to learn a new trick. If you don't graph it, you're going to have a hard time learning the new trick. I'm just giving a very vague sketch so I have something to mark on and point at and all of that. Okay. You got your graph? Slight issue. Can you see all of your graph? If you're like mine, you can't see all of your graph. Now, I've got a trick to help manipulate this. Because here, it is important that I see all of my graph here. Or at least for you guys as beginners. So first thing I'm going to do is I'm going to say, okay, let's zoom out. So I'm going to go to zoom. I'm going to go number 3. I'm going to hit enter once. And then now it's saying zoom out. That's kind of asking a question. I'm going to hit enter again. And now it actually zooms out. Only problem with that is it's kind of zoomed out too far, isn't it? So now I'm going to follow up with a Z-box.
What?
I taught Z-box last week. Or week before. Maybe Tate wasn't here because he's giving me this crazy look. Did I teach Z-box?
Yes. Yeah, I think so, yeah.
Okay. I don't know who was here or not here, but I know I taught it. So Z-box, number 1. Are you guys ready for Z-box? Remember, this is you're making a box around what you want to zoom in on. So I'm going to go, I think I'm going to go down to the left. And I'm going to get, so I'm left of my graph and below the lowest point. Hit enter on this point. and then draw your box and go to the diagonal corner before you hit enter again. So now I'm going to go up and right some. And you just need to make sure you get above wherever that inside curve is, which I can't really see, but I'm going to guess here, and I'm going to hit enter. Ah. Can I see all the important features of my graph now?
Yeah.
Okay. And yours may not look identical to mine because your box may not have been identical to mine. Because here's the deal. It's asking us to find the values of this. So, what's the first thing I can find? What is this? A what? Okay. This is an absolute minimum, yes? It's a minimum because it's a low point. It's the absolute. Will my graph ever go lower than this point? No. So that is an absolute minimum. Now, they want a specific value. No tracing and guessing is not good enough. Okay? So, you guys remember that menu where we could find zeros from? So if we go into that menu where we could find zeros from, second and the trace button takes me into my calc menu. Remember this menu? Notice after 0, we have an option of minimum and then maximum. What is it I'm trying to find right now? Minimum. So I'm going to pick number 3, minimum. And just like zeros, it's going to ask me questions. So first question, left bound. So if I'm trying to find this minimum right here, I'm going to move my cursor to the left side of that minimum. It doesn't matter how far left of it, but left of it. And then we're going to hit enter. Then it's asking me right bound. So now I'm going to move my cursor to the right of that minimum spot. And I'm going to hit enter. And then it asks me for a guess. You can leave your cursor right there and hit enter, or I can go back to the area of my minimum and hit enter. Does your minimum match mine? It should. It should be exactly mine. Negative 2.06 and negative 24.06 is what I'm rounding mine to. Did we get it? Did we figure out the calculators? That was a whole lot easier than teaching zeros. Now, are we done with this problem?
No.
No. Because what else do we have?
Local.
We have some locals. What's this piece right here? That's going to be a local max. So, repeat your process. Go in and find the local max. So start over with your menu. Second, and the trace button. This time, though, you have to know what you're finding because you have to pick min versus max on these calculators. This time I'm finding a max, so I'm going to go to number 4. Same questions, though. Left bound. Just the left of that mountain. Hit enter. Right of it. The right of that mountain. Enter. Guess. We're going to go back to the guess and hit enter. Your max should match my max exactly. I'm going to round to 0.46 and 1.32. Now am I done with the problem? No, I also need to find, what is this last one? A local min. It's not the lowest point, so it's not absolute, it's just local, and it's a min. Second, calc. Going to number 3, minimum. So left bound, just need to be left of that little valley, enter. Right bound, need to be right of that valley, enter. Yes, I go to the bottom of the valley, enter. And again, your minimum should match my minimum. Approximately 1.60 and negative 1.77. Okay, now, I will tell you, I'm not exactly sure how the book asks for or what the answer key will say. However, if we want to get nitpicky, if they ask you for the where does the max or min occur at, they're asking you for the x value. If they're asking you what is the max or min, which I think is what they do in this homework, I don't remember, they're asking you for the y value. Now, in all honesty, I am fine if you just put the ordered pair. But realize there's two different questions. Where does the min or max occur at? That occurs at the x value. What is the max or min value? That is how high or low does it go? That is the y value. Okay, so that's a new little trick on your calculator. Very similar to zeros, which if you remember how to do zeros, it's a piece of cake. Okay, page 93, 22 through 46 evens, and you guys have a couple minutes. Like 6 minutes, technically. Crazy, I know.